Okay, so welcome to the next lecture, which is on black body radiation. So what I begin with is, so I mean, as you might know, that black body radiation, or Planck's derivation of black body radiation in 1900, it was mathematical derivation to fit the nature of the energy density of a black body versus omega. Uh, that was also the advent, one of the first uses of StatMech, uh, and also the advent of quantum mechanics, in the sense that he was the person who theorized to match the curve, the distribution of energy versus omega of a black body radiation of the curve, to say that energy is quantized. The energy of a photon is an integer multiple of a certain quantity, and this, in the future, with suitable developments of Bohr and Schrodinger and so on and so forth, there are too many, including, of course, Einstein, led to the advent of quantum mechanics. So that's the one-line story, but let's start from the beginning. So what I refer to is the Book of Rife, figure 9.1, 9.13.1, and what is plotted there is the energy density per unit area. So energy density normalized by T to the power 4, and there's a certain constant which later we will find and derive, and that constant is pi square C cube H cross cube K to the power 4. So this K stands for KB to the power 4, though the value of KB was discovered much later. And at different temperatures, if one takes a black body, and you must have already heard of what is a black body, we'll discuss it very briefly. So if one takes a black body and plots the energy density versus eta, so eta is h cross omega by kbt. So for different frequencies, so for various values of this ratio, this is an energy unit, there's an energy unit, and eta is a dimensionless unit. So you choose different values of suppose kbt, and vary and look at the energy density for different values of omega. Then choose a different kbt, and again plot energy densities as a function of different values of omega, the frequency omega of light, of the black body radiation which is coming out from a black body, and you plot this constant into the energy density by T to the power 4, and you get a universal curve, which the nature of which in terms of eta is eta cube upon e to the power eta minus 1. Yes. And the question is, can we understand the functional form of it? And this might be the functional form of it, but to get this curve, one has to develop a theory. What does developing a theory mean? Develop a set of principles, a set of rules, a set of assumptions by which you say that light of nature, matter behaves. And if you have some microscopic set of assumptions or some postulates about how matter behaves, light matter interaction behaves, then the larger thermodynamic quantity that you measure is this quantity as a function of h cross omega. So the question is, can we make the right assumptions about the microscopic nature of light matter interactions to explain this, and if we are able to explain this correctly, then we also have access to an understanding of the microscopic nature of uh, matter, light, whatever. So that's the big picture. So that's the big picture. With this, I have already explained this curve, and as I go on, as in the introduction, some of the information or some of the knowledge is also taken from this particular website, Galileo Phys Virginia.edu, classes 252, blah blah blah. So please refer to that. I have taken some information from there, and I need to cite that place. Okay, so let's start with a bit of history. Why did people at all became interested in the idea of black body radiation? What is the concept of black body? How did it originate? So what was happening in around 1859 or 1850s? By the way, that's also the same time that we had our Sepoy mutiny, and the British took over India and made it its kingdom till India became free. But so that's the same period. So while that was going on in India, there were other things happening within the scientific community in the world. And the questions that we humans were asking, that how do heated bodies radiate? So people already knew that atoms have charges. Due to the Maxwell's work, people already knew that if atoms and molecules vibrate, they might vibrate more at higher temperature, and dipole oscillating charges emit radiation. So these were some ideas which had already been developed, and the question was, what would be, so as atoms and molecules vibrate, and if they vibrate more at higher temperatures, what would be the nature of radiation, or what would do with the energy spectrum? So these were the kind of questions they were asking. Now different materials have different um, atomistic structure, they have different molecules and so on and so forth. So they wanted to make an ideal system, look at an ideal system. And in 1859, Kirchhoff uh, postulated, first of all, he developed the idea, he gave the idea of a perfect black body, and the perfect black body can be generated by making a box, cover it with soot, and making a small hole, which you might have already read about. But it was seen, though there was this concept of a perfect black body, even all material given a certain temperature have a particular radiation spectrum. Um, even the even the light which comes out from the sun, the surface at 6,000 degrees centigrade, and that has a certain energy spectrum. I mean, the way we see light, the visible light, of course, that's the peak, and that's why we can. So it gives out the maximum amount of light, the surface of the sun at a particular frequency, and that actually matches with our eye frequency. And by measuring the spectrum, we also get to know about the surface temperature of the sun. But anyway, that came much later. But people were generally discussing about what is the idea of a concept of a perfect black body. Can one define something? And then at some point of time, Kirchhoff, from thermodynamic arguments, he also observed or mentioned or articulated that a body, so in a room you could have many different bodies, some metal, some wood, some I don't know, black, white, or all sorts of things. So he also came up with the idea that a body which emits radiation at a certain kBt, and nu, would have exactly the same absorption coefficient. So emission coefficient, by giving out light, and its absorption coefficient, that the amount of light that it absorbs per unit area per unit time, at a particular frequency in kBt, they have to be equally exactly the same. If not, a material would keep absorbing heat because it has a better absorption coefficient, and it could become spontaneously hotter, which would break the second law of thermodynamics, right? So from that, you can argue that the emissivity and the so the amount of heat absorbed and amount of heat uh, emanated, radiated at the same temperature in a certain frequency range, they have to be the same. And once this idea of a perfect black body was uh, mm, it was just 1 second. Yeah, once it was actually uh, postulated, then over the next 20 years, the people did experiments, and Stephen law was postulated in 1879, where he observed that the power means power per meter square, power itself per unit time, energy per unit time per meter square emanating from a black body actually was proportional to T to the power 4. So this is called the Stephan's law. And the proportionality constant here observed to be 5.67 into 10 to the minus 8 watts per meter square to k to the power 4. So you increase temperature, there's more total amount of energy which is emanated, and total amount of energy emanated goes as T to the power 4, right? The other observation was, I mean, they had a better idea of the entire spectrum, so they could measure the energy density at different values of the frequency. And at some point, I think in 1893, they saw that the peak, so they saw that at different frequencies, there were different intensities. First of all, there were different energy densities. And the peak of the energy density always changed, the frequency was proportional to temperature, okay, which was called the Wien's displacement law. Now, in 1884, from statistical physics arguments, Boltzmann had some explanation for sigma to the to the Stephen's law, where he observed that the power, the total energy, yeah, energy per unit time per meter squared, which was being emanated, increased as T to the power 4, but it was not a complete theory. Just to give an idea of the some of the numbers, so I want to tell you that if you take some black body at 1000 Kelvin, um, so that's the point that you start seeing red light, so that the peak of the distribution is approximately red, and it corresponds, we can start seeing that it is emanating heat. And that's because, I mean, emanating light, we can see the radiation, the red spectrum, and 1000 Kelvin approximately, and that corresponds to 4.3 into 10 to the power 14 uh, kilohertz. Sorry, 10 to the power 14 hertz, actually, right? And if you convert this frequency from lambda nu equal to c, where c is equal to 3 into 10 to the power 8 meters per second, the speed of light, then you can calculate the lambda max, and that will come out to be around 700 nanometers. And remember, that's the amount of that's the frequency that we can start seeing. And of course, if you increase it, the wavelength shall start becoming smaller. It shall go up to 400 nanometers, and that's the blue spectrum, or the frequency will start increasing. So the peak. So we are, of course, our eyes is more sensitive to the peak of the spectra, right? So as we increase the temperature, it will go up, and we will see, we will get to see, we'll get to see higher, the blue color essentially, right? Which will correspond to lower, which will correspond to lower frequency, higher frequencies or lower wavelengths, right? Just to give you an estimate, that at room temperature, the peak of the spectra is, I mean, you can just calculate it if you believe in Wien's displacement law. That's an experimental law. So the maximum, uh, so at temperature, room temperature of 300 Kelvin, which is one third of this, the peak of the spectra is at 2.1 microns, right? The lambda max, the wavelength corresponds to 2.1 microns, and our eye, of course, can't detect it unless the temperature goes to higher temperatures, and then the peak, we can detect the peak of this spectra. Of course, if everything was much more brighter, we would be able to see it, but when we heat it, we start seeing it once it reaches 1000 Kelvin, which is like 700 degrees centigrade. So these are the numbers, and numbers are always good to know. The other thing I want to illustrate, which is again taken from that website, that while we are aware about this law, I want to plot the energy density versus frequency at two different temperatures where so this is a schematic diagram, of course, and this is at temperature T and this is at temperature 2T, double the temperature. So the schematic diagram at temperature T, if it looks like this, right, I mean, there's this schematic diagram, then if you just increase the temperature, the energy density power per unit area would basically increase 16 times. So this energy density will look more like this. And I'm not saying that this is the area under the curve is 16 times, but you see the difference. That's a huge difference in energy density that you get just on increasing the temperature from T to 2T. The other thing you should realize is, however, I have been trying to keep it careful that the frequency at which you get the maximum of the energy density, that just increases by a factor of 2, but the total area under the curve is much bigger, right? So that's the broad meaning. And yeah, so the other importance of this black body radiation is because he wanted to, so there was some experimentally measured curve, and after Planck did his derivation to fit it, uh, that was the first time that he had to use a fit parameter, and that was how the first estimate of the Planck's constant H was arrived at. So, statistical physics did play quite an important role even in the development of quantum mechanics. That's the message. Okay, so let's get further ahead. Uh, so we have to apply quantum statistics of ideal gases. I will just briefly go through some other quantity and then we'll come back to black body radiation. This was just the motivation of why we are studying black body radiation. And you might already be knowing that, I mean, all basic matter, the constituents of matter can be broken up, can be divided into two parts, the so-called bosons, right, and fermions, and classical distinguishable particles. Of course, at the microscopic level, there's nothing which is classical and distinguishable, but at the macroscopic levels, we have. I mean, we can distinguish whether an object is like this, and we can distinguish between two objects, but microscopically, if two particles, the positions of two particles were exchanged, right, you wouldn't be able to uh, distinguish between them. Now you know that fermions have the property that the two fermions cannot have exactly the same quantum numbers. So in a particular quantum state, there can be only one fermion. On the other hand, you can have multiple bosons, right? So here, this is basically a quick description of if you had just two particles in three quantum states, what would be the different ways of arranging them. And if you had classical particles, if these particles were classical, then in any particular state, you could put both of the two particles, AB, 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 and then there are various ways of distributing them. And if you calculate zeta, the what is zeta? It's the probability that particles are in the same state divided by the probability that particles are in different state, then for classical particles, you will get zeta to be 3 by 6. For bosons, so you will get three states where particles are, so there are three microstates, three different ways where particles can be in the same energy level, say, or quantum states, say. I mean, there are two particles in three quantum states, and three ways such that they are in different states. And on the other hand, for muons, you can't have two particles in the same quantum state. So in this sense, zeta is a measure of how much particles would tend to spread over different quantum states. So for classical, it is 3 by 6 zeta, and for bosons, it's 3 by 3, which is 1, and here this is 0 by 3. Right, so it distinguishes the tendency of particles to spread over different quantum states. Of course, in reality, you will find only these two. The other thing that I want to say is, so coming back, so we have to use the quantum statistics now, and the idea that photons are bosons. Now, why photons are bosons, that's a different topic, but here we are going to accept that photons are bosons and do the statistical mechanics about it. Now suppose there was a set of quantum states corresponding to energy epsilon 1, epsilon 2, epsilon 3, epsilon I, up to epsilon n, and there are a certain number of particles, and for photons, particles can be created and destroyed, so there can be absolutely very different number of particles which can occupy different energy states. Right now, so a particular energy level epsilon 1 has n1 photons, say. A particular different energy level has n2 photons, and so on and so forth. Note, by writing down the energy in this expression where n1, n2, n3 are integers, we are already thinking in terms of a quantum that the energy of the entire system can change in units of only epsilon 1 or epsilon 2 or epsilon 3, and so on and so forth. So you can't have a fraction. So you can't have a, so if one more photon is added at energy epsilon 1, the energy change, the quantum of energy change is epsilon 1. If two more photons are subtracted from this, then the quantum of energy change is 2 epsilon 2 and nothing in between. So, but by just writing down the expression of energy in this manner, we are actually assuming the quantum nature of light, yeah, and that's what Planck assumed, that energy can be only added in discrete quantities. Of course, what is the values of epsilon 1 and epsilon 2 and epsilon 3, etc.? We will come to the discussion, but what we will first do is, suppose you have a black body and within which you have a certain number of photons, where some of them are in energy level epsilon 1, epsilon 2, epsilon 3, and so on and so forth. And it has some temperature. So you can calculate the partition function of this system, where the total number of particles is not conserved, right? I mean, it can have absolutely 0 to infinite number of photons. Of course, if the system has an extremely high energy, epsilon r is the energy of the entire system, right? So that corresponds to a microstate. Specification of the values of n1, n2, n3 will correspond to a microstate. Of very high energy microstates will be penalized. The probability of accessing those will be very less. Well, it will also depend upon beta being 1 by kBt, and if we have higher temperatures, the system can access higher energy microstates. The same principle of StatMech, but if one assumes on principle that the number of photons that can be there in epsilon 1 can vary from 0, 1, 2, 3, 4 up till infinity, In principle, you can have infinite number of photons, because the black body is in contact with a heat bath, and that's why you are able to define your temperature and so on and so forth. So then in principle, we can write Z, the partition function, as a sum of so you're summing over all possible microstates, the different values of R that are possible, and that is e to the minus beta n1 epsilon 1 plus n2 epsilon 2 plus n3 epsilon 3 and so on and so forth. Now note that the number of microstates here possible are absolutely infinity, because one microstate might have one of these particles and different values of n2, n3, and n4. Another will be this will have 2, and n1 can vary from 0 to infinity. Similarly, n2 can vary from 0 to infinity, and n3 can vary from 0 to infinity, right? And they're not interacting with each other, so you can just split them up into summation of n1 going from 0 to infinity e to the minus beta n1 epsilon 1. And if photons can be added at the second energy level. Now, how these photons are being added, that is not being discussed. We're saying that somehow there is some quantum mechanical process which was even discovered later, much later, by which these photons were being released. But mentioning that, you have only n1 number of photons with energy epsilon 1 and nothing in between, and epsilon 2 and epsilon 3 and so on and so forth, a continuum, right? You're already here putting in the discrete nature of the energy or the frequency of light. So that's where it is going in, and the values of epsilon 1, epsilon 2, epsilon 3 will be calculated soon after. So the point is, you can, to calculate this partition function, you can do a sum over this. This is a GP series, right? When epsilon equal to 0, when n1 equal to 0, then e to the power 0 is 1, and n1 can have 1, 2, 3, 4, 5 up till infinity, and the infinite GP series, if you add it up, you'll get 1 upon 1 minus e to the power minus beta epsilon 1. So this is the, so this is the, this will be one term, and 1 upon e to the 1 upon 1 minus epsilon e to the power minus beta epsilon 2, and 1 minus e to the power beta epsilon 3, and so on and so forth. So this will go on, whatever energy levels are there. So what is the point? Then if you take log z, right, then log z will be a sum of log terms, because this was a product. So r equal to the sum is over all possible microstates, and each energy level epsilon r, right? So epsilon, so r stands for the energy epsilon 1, epsilon 2, epsilon 3, epsilon 4, and each is going to contribute ln 1 minus e to the power minus beta epsilon r. R is the number of energy levels of the system. And if you know this, then you can actually calculate the average number of particles in a particular energy level S, and that is given by minus 1 by beta del L epsilon ln of Z. And why is that? So basically, if you have to calculate that, then the n bar S in a particular energy level S will be given by 1 by Z, number of photons in that energy level, and the probability of accessing that microstate. So remember, here you have n1 epsilon 1, n2 epsilon 2, all of these, because that constitute a microstate, right? Because suppose S is 3, right? Now with 3 photons in epsilon 3, in energy level epsilon 3, you can have a variety of n1, n2, n3, n1, n2, n4, n5, n6, right? But all of those microstates correspond to ns equal to 3. Now, if ns equal to 4, so S is 3. Now you could also have 4 photons in energy epsilon 3, and then with the energy of 4 photons in energy epsilon 3, you could have a very large number of different combinations of photons in other energy levels, right? So basically, you're summing over all of them. So n bar s is 1 by z. How many photons are there in energy level, say 3, and all different microstates which have the same energy level. This in turn can be written as, it can be written as, if you take a derivative with respect to epsilon s, right? Then you will get ns. So you will get exactly this expression. So you can just check it out the way you do it. And then n bar s can be written as 1 by beta del del epsilon s ln of z, and you can just try that out actually. So this 1 by z will give this ln, because we'll write del del beta 1 by z del del beta, sorry, del del epsilon s into 1 by beta, and that will be converted, right? And you have already calculated the expression of z. So this can easily be calculated. So here I have done the n bar s equal to 1 by z sum over all r minus 1 by beta del del epsilon into e to the power. So this is the energy of a particular microstate, and you're summing over all possible microstates. So and different microstates will be defined by different combinations of n1, n2, n3, and then this will give 1 by z into minus 1 by beta del del s into the partition function, and from there you get n bar s equal to minus 1 by beta del del epsilon log z, right? So if you already have an expression for ln z from here, then you can just calculate the n bar s, and that is that on doing the differentiation, you will get minus 1 by beta e to the minus beta epsilon s beta, this term, right? And this in turn, this beta and beta cancels, so this can be simplified into 1 upon b to the power epsilon s minus 1, right? So we have already got some part of it, and this sum over different microstates relied upon the GP series with integer. It relied on a GP series, which in turn required the quantum nature of the energy spectrum. So that's where we get it, right? So that's how it was first thought of. Now the question is, okay, fine, we have got this, but what are going to be the values? What are the allowed values of epsilon s? So that's the question we're going to ask next. And to do that, so this is taken from Rife section 9.3. One assumes that you have an assembly of photons in thermal equilibrium at kBt. The black body is at equilibrium at temperature of kBt in a box of volume V equal to L cube. You could take a cubic box, or you could take L1, L2, L3, or you could just generally take a general any arbitrary shaped box as well, and you assume that photons are absorbed and emitted by the walls at temperature kBt. Mechanisms of emission and absorption is unknown, or this is not the part of discussion of this class. It's a quantum mechanics class. How would they interact? What would be the Hamiltonian? But we say, okay, if it is emitted, what is the spectrum? What is the distribution of energies? That's what we are going to discuss, not mechanisms of emission, which is quantum mechanical in origin. And we know, I mean, because experimentally it was known that the distribution of photon energies depends on T, and our aim is to figure out the distribution of photon energies. This photon statistics, what is the frequency, how often do you have certain particular photons of certain energies, or between epsilon and epsilon plus d epsilon, or correspondingly nu and nu plus d nu. Yes, so and we are considering radiation, electromagnetic spectrum, collection of photons, and all of that. So we shall say that the photon state, so this is now from Arrive section 9.13, the photon state can be specified by the wave vector and moreover the polarization state. So electromagnetic radiation, Maxwell's law had already developed, but we want discrete values of energy. And what is the idea that we're going to use to get discrete values of energy? So that's the topic of today's discussion. Um, and also it is known that light can be polarized, so the two polarization state. The assumption is that characteristic, the energy spectrum is specified by n bar s. How many photons do you have at low energies? How many photons do you have at medium energies? How many photons do you have at higher energies? So if this n bar s changes as you change temperature, you will get a different spectrum. So we are really interested to calculate the number of photons in energy state S, which we already got from here. And now our destination is to move that how are the values of epsilon 1, epsilon 2, epsilon 3, how are they decided, right? So the point we are trying to say that okay, we have to calculate the number of photons in energy state S and how they are going to change, but we also which we have already have an expression for, but the question to ask is so it's not that energy levels are uniformly distributed across different values of energy, right? So at higher energies, you might have more number of quantum states. So the idea what one could think is that when we were talking even of the ideal gases, if you increase the energy, the number of microstates accessible is much more, right? That's what we argued at that point of time. Here, we are not talking about microstates. Microstates is defined by the combination of N1, N2, N3, N4, and so on and so forth. But the number of quantum energy levels available between epsilon and epsilon plus d epsilon, that could increase with epsilon itself, right? So you could have a higher density of states at higher energies. Agreed that at higher energies, you have a lower probability of accessing very high energy microstates. But if there are many microstates available, if there are many quantum levels available at high energies, then the probability of accessing those set of quantum levels between epsilon and epsilon plus d epsilon become probable, because the probability decreases, but the number of quantum levels or the number of microstates increases. So quantum levels and microstates are different. N1, N2, N3, N4, N5 decide as microstate. But suppose there are many quantum levels available between, say, epsilon 14 and epsilon 15. Or between between epsilon and epsilon plus d epsilon, there are many energy quantum levels available. So suppose 14, so epsilon 14 to 25, right, correspond to a small value of d epsilon, and there are more and more quantum levels being available. The probability of accessing each of them might be low, but if there are more quantum levels available, the product of the probability into the density of states can become a finite number, and hence you can find a peak at the certain value of energy as you increase temperature. In fact, the probability keeps on increasing, the quantum levels, the density of states keep on, the probability decreases with increasing energy level, the density of state increases. So if you take a product of an increasing function and a decreasing function, you're likely to find a peak. I mean, at some point, the product of the two will reach a peak. Of course, it will depend on the nature of the functions as well. So that's what we are after. So we have already calculated the mean n bar s, and we can similarly have the probability of occupying epsilon energy is now energy epsilon. Now we are after the density of states. How many quantum levels are there between epsilon and d epsilon? So for that, what we assume is basically that the energy of an electromagnetic field can be written in terms of h cross omega, and this in turn, so the energy can also be written as Cp. Is that correct? So P is h cross k. K can be written as omega by C. So basically, yeah, the energy I think can be written in terms. So P, this modulus P is h cross k. This can be written by omega by C. Yes. Yeah, h cross by, yeah. So it can be written like that. So the question is, what are the frequencies allowed? What are the wavelengths allowed? So these are the standard set of formulas which you might be familiar with. P equal to h cross k, k equal to omega by C, and k is 2 pi by lambda, which means 2 pi by nu. Lambda, I think, is substituted. Yeah, lambda is substituted as mu c, correct? That is lambda equal to nu c, let's see by time period. And the question you are asking is how many photons are there between k and dk. Equivalent is asking how many photons are between nu and nu plus d nu, and so on and so forth. And each photon has energy this. So what we say, so typically in quantum mechanics, if you have gone through a course, how does discretization of energy level appears? It appears from the boundary conditions. If you have a differential equation, or even if you have a plucked string, not all frequencies are allowed, and which frequencies are allowed. Discrete frequencies are allowed from this struck spring and so on and so forth. If you have these nodes and so on and so forth. So we are going to apply similar ideas to get discrete energy levels for the light waves. So now if you say that the box is significantly greater than the wavelength of light, and then you are asking what is the largest wavelength which is allowed, and the largest wavelength which is allowed. I mean, so there are light at different frequencies, but only a certain set of frequencies are allowed only for the frequency or equivalently wavelength for which the largest wavelength is allowed. Suppose where the two, so the amplitude is 0 at the two walls. So one of those wavelengths are allowed. So of course it could have something like this. This is half a wavelength, but then you could have a full wavelength, and you could have a three three and a half wavelengths, and so on and so forth. We say all of those are allowed. So that's one way of looking at it. So the question is, so where is the broad question? We are trying to calculate how many wavelengths are there between k and k plus dk, and in general in 3 dimensions, and that will be given by f k d3k, which is basically saying between k vector and k plus dk vector, how many wavelengths are there. And so in 3 directions, we could use using the idea which I just told you, lambda 0 by 2 equal to L, or you could say, well, lambda, I mean, the whole wavelength is, so the entire length can have such a wavelength, right? So any wavelength which is between lambda 0 and 2 lambda 0 is not allowed, by demanding that this wavelength, that this amplitude of the electromagnetic radiation will be 0 at the walls, right? So you get a series of wavelengths which are allowed, and in intermediate wavelengths are not allowed. So correspondingly, you get k1, k2, k3, and this is in 1D, but now you can also generalize it to 3D. In general, a number of states between, say, k and k plus dkx, suppose the number of wavelengths which are there, the number of waves or the states which can be there between k1x and k9x is basically pi by L into 9 terms. So if we take such a discretization, in general, if we take k1x and k1 plus dkx, then that will correspond to a certain delta nx. How many wavelengths are there between k1x and k1 plus dkx, right? Now, depending upon what your value of k is and what your value of dk is, you can see that the allowed values of k for these set of boundary conditions, and we're going to soon change the boundary conditions, by the way. The allowed the vectors which are allowed are 2 pi by L, 3 pi by L, 4 pi by L, and pi by L. So basically, it increases by pi by L, and the number of wave vectors between k1x and k1x plus dkx is basically pi by L into del nx, and then del nx, the number of wavelengths, basically depends upon L by pi dkx. Now, if you choose a different boundary condition, then you can also get delta nx equal to L by 2 pi into dkx. And what is the scenario corresponding to that? So if you put these boundary conditions, then you will get L by pi dkx equal to dnx. But Rife also considers, and that would be possible if you have a cubic box, but in general, you can take a less restrictive boundary condition which says, so if we took the boundary conditions that psi equal to 0, psi being the wave function, the wave, the wave, so that is equal to 0 at x equal to 0 and x equal to L, then you will get dkx equal to pi by L into dn, or dnx if you like. And of course, if you take in 3 different directions, then delta nx, delta ny, delta nz, then you'll get the total number of vectors allowed. But if we, on the other hand, we have a less restrictive condition, we don't demand that psi has to be 0 at x equal to 0 and has to be 0 at x equal to L, but in general, say that psi at x, y, z has to be equal to, it need not be 0, but just equal to psi equal to x plus lx, y, z, and psi at x, y, z equal to and not equal to 0, psi equal to x, y plus ly, z, and so on and so forth. Then what we will get is del k equal to 2 pi by L, because they have to be equal. So you can check that out, that Ly has to be 2 pi n and so on and so forth. So from there you get, yeah, exactly. So from there you get a delta k equal to 2 pi by L delta n, and delta n equal to L by 2 pi into dk. So that's a much more restrictive condition. So that corresponds to really L by 2 pi dkx equal to del nx, right? So that's what we get. In general, we can ask about, so between kx and k plus dkx, ky and k plus dky, and kz and dkz, how many total number of levels are there, and that will be Lx by 2 pi dkx, Ly by 2 pi dky, Lz by 2 pi dkz, which can be written as 1 by 8 Lx, Ly, Lz, which is basically a measure of the volume, a pi cube to dkx, dky, dkz, right? So we get 1 by 8 b by pi cube into d3k, if you like. So we can already start asking how many energy levels or quantum levels are there between k and k plus dk. Now this is in vectors d3k, but in general we can also say I don't care about which direction it's moving, because it's likely to be moving in all directions within the black body. I just care about between k and k plus So basically modulus k and k plus dk modulus, right? Because this is the thing which is deciding the energy. K is uh, so k is related to omega by c. So you basically want to see how many levels are there between k and k plus dk, and correspondingly, uh, so modulus k independent of the direction, and correspondingly you know how many levels are there between omega and omega plus d omega, right? So if k is equal to omega by c, then dk is equal to d omega by dc. So it's the width, how many, what is that range of wave vectors modulus, or range of frequency modulus, that how many energy levels do you have. And if you also want to account for the two polarization states, then you have to multiply by 2. So those are the number of levels that you have. And then things become very easy. It's basically the mean energy between omega and d omega per unit area and per unit time, and so on and so forth. Well, that is not here yet, but it's basically the average, how many particles, how many photons are there in a particular energy level, which depends upon kBt, because we already got that expression. So we had that, so we got the expression n bar s equal to 1 upon beta h cross omega minus 1, where omega was 2 pi nu, and so on, and so on and so forth, into the number of states. Now, this is not microstate, a number of energy levels. How many quantum states are there between omega and d omega, which we found by quantizing k, and k is related to omega, right? We got discrete values of energy by using such principles, since k was discretized, as a consequence of which omega is discretized, as a consequence of which you can count how many energy levels, what quantum levels are there between omega and d plus omega. So the mean energy between omega and omega plus d omega, this is the quantity that we were after from the, because that's the thing that they had plotted in the experiments, is then now average number of particles in energy level s into density of states between that level s into h cross omega, right? So how many particles, number of microstates into energy of the thing. So as a consequence of which we easily get, now just substituting, this is here, h cross omega is here, and the density of states comes out to be v into omega square. So this was this k squared dk, right? Where there's, yeah, so v into omega squared d omega. Now there was an omega sitting here, that becomes omega cube, and yeah, there was a dk also. This gives d omega by c. So hence we get this volume is already sitting here, y pi cube, right? This 4 pi and 2 cancels with 8. I mean, not the pi. So this pi cancels here with, so as a consequence, we get v h cross pi square c cube. So there was a c here, c square here, and a c extra here. That's where the c cube comes from. So we get v h cross pi square c cube omega cube, because this omega and this omega square, omega cube d omega. And if you simplify it, just check whether this expression is correct. I'm not sure, but this is, I think, correct, right? And then you can write down the so this is the energy between omega and d omega, and this is now the energy density. If you take this volume of the box here, and this is the quantity that you get with the prefactors matched. Now, if you remember, control, let's see. So here you have h cross. If you had to fit the curve, energy density per, you have to fit the energy density, yeah. coming from the entire black body radiation, and you want to fit the curve, then you would have to fit h cube, right? You can do it at different temperatures, so that so you define your h cross omega here, right? Of course, the value of kb was also not known, so I guess they had two fit parameters, or I don't know, or they might have just plotted. Yeah, I don't know how they did the fitting, but that's how you have h cross sitting here. So there was some fit parameter, and that fit parameter value came out to be, which was later decided to be Planck's constant. Now, just to look at it, the energy density, if you convert, so what has been done is all the constants has been taken to the left hand side of the equation. So you have energy density d omega into these constants, right? So what is this u bar? Uh, Okay, so this energy density is u bar. All the other things, when you substitute here, because you had omega cube sitting here, you get a lot of, and d omega, you essentially get from omega cube. So omega equal to eta kbt upon h cross. So when you substitute that, yeah. So when you substitute that, you get eta cube d eta e to the power eta minus 1. Yeah, you get all these terms. You can check it out, and then you can plot. So basically, energy density is here, and into the other terms, that comes out to be eta cube into e to the power eta minus 1, which was the uh, term which we started out with, which was plotted in Rife. The first figure, you can go and have a look. So just to give you an idea, the function has a peak at eta max approximately equal to 3, not exactly equal to 3, but that's a working number which you could remember. So if T changes, if temperature changes, the peak will also, the position of this, the peak will also basically change, and the peak always remains at 3. So basically h cross by omega 2 by kbt by 2, well, the peak will always be at 3. So if omega t changes, omega 2 is also going to change, which is basically Wien's displacement law, right? So h cross omega 1 by kb t1 equal to h cross omega 2 by kb 2, which is, and the max, and the corresponding, from here you can get the max value, the frequency at which the intensity is the maximum, right? And moreover, if you integrate over all frequencies, right? So then what you would get is s cross pi square c cube kbt to the power 4, and you're integrating over essentially eta for the frequencies, and this quantity has a fixed value pi by 4 to the power 15, and you here, so the total energy emanated, and you can divide it by total area per second, and so on and so forth. That is proportional to T to the power 4, which is the so-called Stefan's law. So from here you get your Wien's displacement law. From here you get your Stefan's law, and basically that's the end of black body radiation module. So this is how statistical physics, discretization of energy density of states was used to get the Planck's radiation constant, right? And you can look up your book to see where was this Rayleigh Jeans catastrophe. There's some other history. There were some other theories which were proposed before Planck came out with this general expression which explained the entire range of the spectra. That's history, and you can look it up in kinetic theory books. So with that, I shall stop the recording.